So in this lecture we'll try to understand what is the solution of ISI. In the previous lecture we tried to understood what was the reason of ISI. So the main reason of ISI was that when a pulse of the duration TB, which actually is band unlimited pulse, is passed through a band limited channel, then at the output we get a band limited pulse, and which causes the expansion of pulse in the time domain like this. So this pulse is interfering with another pulse in this region. This region is meant for some other pulse. That is why ISI was occurring. Now, what is the solution of ISI? So the problem is the band unlimited pulse is passed through a band limited channel. Question is, can channel be a band unlimited? No, channel cannot be a band unlimited because it is not practical to have a band unlimited channel. So the solution lies in having a pulse which is a band limited pulse. So let us see here. So what we do is we select a pulse which is shown here. So in this case we choose a pulse of the height 1 by RB. Okay, and this pulse is of the duration, that is of the bandwidth RB by 2, that is the Nyquist bandwidth, which is the minimum required bandwidth. And if I take the inverse Fourier transform of this pulse, that is PF inverse Fourier transform, then I will get this pulse, that is sin C pi t RB, with a 0 crossing at TB, 2 TB, 3 TB. And since I have taken the height as 1 by RB, that is why the height would be 1. In other words, what I have done is I have chosen a pulse PF to be a band limited pulse of the bandwidth RB by 2. It has its inverse Fourier transform, that is this pulse. So this is your PT. So if I do this way, then ISI can be avoided. How it can be avoided? Because what I am doing is I am transmitting a band limited pulse through a band limited channel. So my channel is band limited as seen previously, that is from minus omega c to plus omega c. So if my omega c is less than RB by 2, then this pulse PF can easily be transmitted through the channel which is your HF. This is the solution. But the problem is, what I am getting is a sinc function in the time domain, and this particular pulse in time domain is basically a time unlimited pulse. So this is time unlimited pulse. Now you may ask one question as to how ISI is avoided using this solution. Now in this case it is clear that because the problem is this particular pulse is time unlimited now. Now question is how a time unlimited pulse will not cause ISI, because it itself is expanded pulse. Now it is important to mention how it avoids ISI. It is very important to see how it avoids ISI. Now for that, what we do is we see this diagram. So this diagram is basically drawn for two particular bits, 1 and 1, and then there is another bit that is 0, 3 bits. So for first one we get this pulse, that is with the first 0 crossing at TB, second 0 crossing at 2 TB, and for another one we have this pulse, and for another 0 we have this pulse. Now as can be seen from here that these two pulses are interfering. However, the interference at threshold point, at the point at which we will take sample. What is the point of taking sample? In digital communication, what we do is we take sample at optimal sampling instant and compare that sample with the threshold lambda. If my sample value s is greater than lambda, I decide in favor of bit 1, else I decide in favor of bit 0. So now in this case, what is happening is there is interference. However, at sampling instant, that is TB. Now you may ask why TB is a sampling instant. That we'll see in unit 3 as to the optimum sampling instant are NTB. The reason that we'll discuss in unit 3 when we will discuss the optimal receiver, that is a match filter based receiver considering additive wide Gaussian noise. Now if TB is the sampling instant, then at this sampling instant, then the effect of pulse 1 is 0, okay, and the pulse 2 is maximum, that is 1. So if I sample at this particular instant, then I have the effect of only the second pulse. The effect of first pulse is 0. Similarly, if I sample here, then the effect of second pulse on the first pulse is 0. In the similar fashion, if I sample at 2 TB, then the effect of first pulse and second pulse at t is equal to 2 TB is 0. So it appears that these pulses are interfering. However, at sampling instant, that is t is equal to plus minus NTB, this interference, that is ISI, is 0. Interference from the one pulse on the other pulse is 0. That is why this is causing 0 ISI. This is the solution of ISI. This particular solution is referred to as Nyquist first criteria of 0 ISI. Also, this is called as ideal solution. We'll discuss why this is called as ideal solution. But before that, I'll repeat again. What we have chosen is to make ISI 0. We have kept pulse PF a band-limited pulse of the bandwidth RB by 2. This is its inverse Fourier transform. That is a time unlimited pulse. And since at sampling instant the interference, these pulses are 0, that is why when we take sampling instant, then interference effect is going to be 0, This is how it is avoiding ISI, and this solution is called as a Nyquist ideal criteria of 0 ISI or Nyquist first criteria of 0 ISI. The same thing can be written mathematically as this. So a pulse which will avoid ISI or a 0 ISI pulse PT can be written as PT equals to 1 for t equals to 0, and it is 0 for t is equal to plus minus NTB, that is at sampling instance. So this pulse is called as a Nyquist 0 ISI pulse. This is a mathematical representation of 0 ISI pulse. However, there is some problem with Nyquist ideal solution. So what is the problem? Let us see one by one. So first, as the pulse is extending from minus infinity to plus infinity, so it will take infinite time for reaching at t is equal to 0. In other words, it cannot be generated because it is starting from minus infinity. So in other words, it will take infinite time till it reaches 0. So it is an impractical pulse. This is the first problem. The second problem is it is a non-causal pulse. As can be seen, this pulse is starting in this is the time domain. So since it has its existence in the negative time axis, so that is why it is a non-causal pulse which cannot be practically, which doesn't have practical implementation. And the third problem is even though if I assume that it has practical implementation, but it doesn't have any tolerance of sampler. What I have assumed is this is my sampling instant TB. Practically, there is no sampler which will exactly sample at t is equal to TB. So sampler will have some error in the sampling instant, that is TB plus delta t. It will depend upon the jitter of the clock or this sampling instant at the receiver side. So in that case, if I am not sampling at this instant, if I am sampling at this instant, then ISI will again occur. ISI because of some other pulse will again occur. Or if I am sampling at this instant, that is not exactly TB, it can be plus, it can be minus, then ISI will occur. So what I mean to say, my third concern is that because of timing jitter, my sampling instant will not be exactly TB. Rather, so it is not exactly TB. Rather,